All right, we're back with SQL Workbench J. We've connected to our Abacus data warehouse, and it's still empty, but let's go ahead and take care of that now. I have some pre-prepared scripts, and I'll make those available to you to download so that you can quickly create your own schemas. The first one we're going to build is a dimension table for product. It has typical product columns, a product key, weight, size, unit numbers, stock levels, the type of stuff that you'd find in just about any data warehouse. And this is very common ANSI SQL. Now that that table is created, I can refresh my table list and we can open it up, and right away we see kind of a PostgreSQL nuance. All of my column names have been forced to lowercase. If you haven't worked with Postgres much, that's a pretty common thing. If you want camel case or mixed case or uppercase, you're going to have to put all of your column names into quotes. The default for everything else is lowercase. Postgres, being a Unix-based system, is case sensitive, so frankly I think it's kind of nice that it forces it to lowercase for you. Now we talked about the distribution style and what the default would be. Running this query here, we can see that that dim product table was created with even distribution. So I'm going to go ahead and drop that table and let's recreate it and choose a different distribution style. Now this brings up an important point. You can't change distribution style once it's been created. Your only option is to drop that table and recreate it. So I'll open up this script again, and the way I specify my distribution key is I just pick the key column that I want to distribute by, and I add the keyword dist key. Because product key is going to be the primary key of this table, I'll go ahead and add my dist key to that. So the table's been created, but it doesn't really look anything different. To be able to look inside of the table details, we will have to run some kind of query to pull from the system tables what that distribution key is. Run this again, and now you can see that it is key distribution style. All right, now let's add a fact table. But before we do that, we're going to need to recreate that table just one more time, because as you'll notice, we didn't define a primary key on that table. So I'm going to go back here again, add distribution key, and then specify this as my primary key, because now I want to build this into a relationship. Again, this is all stuff that you have to do at table creation time. You're not going to be able to come in later and add a primary key. So with that done, we can now create the fact table that goes with that dimension, and we'll specify that same distribution key on that same column. This will help with those joins because these two tables will be distributed on the matching columns. Now this one's a little bit different. This primary key is actually a compound key, so you see I use the constraint clause down here below. And now to create the actual relationship between those keys, I do an alter table statement and add that constraint. So now I have two tables, a dimension and a fact table, that are related through a primary and a foreign key, and they're both using a distribution style based on that key. Now there's an interesting nuance that you should be aware of here, and that is the existence of primary keys, foreign keys, and these foreign key relationships are purely to help Redshift with query optimization. They don't actually enforce anything at the Redshift level. In other words, you could have a primary key and insert a duplicate value, and Redshift isn't going to stop you. Now that will probably seem very foreign to people who have worked with pretty much any other RDBMS system. The same goes with a foreign key relationship. You could insert a value that doesn't have a matching key, and it would still let that happen. What this means is the responsibility is on you during your data load and ETL processes to enforce that data integrity yourself. Now this might seem completely ludicrous to some, but there's actually some pros and cons to that. Obviously the con is the potential for data quality issues. So again, you really have to pay attention during that data load and data sourcing process, because Redshift is saying, I trust you. The pro is performance. On inserts and on updates, it doesn't waste any time verifying that those are valid entities. And it actually does have a performance increase. And again, the existence of it is to help during the query optimization process, as it is compiling instructions to hand out to those distributed nodes. So lock that away in your long-term knowledge of Redshift because you don't want to be caught off guard by that fact. All right, we're going to return to our slide deck and talk about those remaining items that gives Amazon Redshift such a great reputation when it comes to large-scale OLAP performance.